Welcome back everyone to this tutorial. So in the last tutorial we learned how to calculate the reflection coefficient at any point x on the transmission line. So if you remember, gamma x, which is the reflection coefficient at point x on the line, is given by gamma naught, which is the reflection coefficient at the load, times e to the minus 2 gamma x. So you can choose x to be any point on the line. Remember that the line has a length L. Every line has a finite length. And if you substitute 0 on this formula, the e term here becomes 1, and you are left with the reflection coefficient at the load. So this proves to us that the formula is valid. If you remember also, the voltage along the line here is the sum of the incident voltage plus the reflected voltage, and it's given by V plus e to the gamma x plus V minus e to the minus gamma x. So remember how we calculate the coefficients, reflection coefficient gamma naught here is ZL minus Z naught divided by ZL plus Z naught. So our next task here is to calculate now what is the impedance at any points on the line. Remember that the line is made out of resistors, capacitors, and inductors. So it's not just a line, it's not just a wire. It's like a component, a circuit component, and it has an impedance. If you look at the generator here, if you look into the line like this, the generator will see an impedance right here. If you look here, for example, you will see another impedance. If you look here, you will see another impedance. And if you look here, what you see is just the load impedance. So we can calculate the impedance. We should be able to calculate the impedance at any points on the line. So how do we do this? Remember how we calculated the reflection coefficient at the load, and remember that this was the formula that we got. So if we now want to calculate the impedance right at any point here, we can use the same formula. We can pretend, for example, if we mark this point here on the load and pretend that everything to the right of this is just another impedance, then we can use this formula here, which says that the reflection coefficient here at x at this point, we say that it's equal to Zin. Zin is the impedance looking in here at this point here, or let's say at this point x. This is at Zin, and so the reflection coefficient here will be equal to Zin minus Z naught divided by Zin plus Z naught, which is exactly the same thing that we do here. So we, instead of using ZL, we use Zin. Because remember, we are pretending that everything to the right of this point x here is an impedance, which is the sum of this impedance here plus this impedance here. So if we use this formula here, we should be able to calculate the impedance. So all we have to do is solve for Zin, and we'll have the impedance at that point. So let's solve this equation here. So we'll multiply both sides by this term here. So we get this is equal to gamma x times Zin plus gamma x times Z naught is equal to Zin minus Z naught. So now Zin times gamma x minus 1 is equal to minus Z naught minus gamma x times Z naught, which is equal to Z naught times minus 1 minus gamma x. And now if we divide both sides of the equation by gamma x minus 1, then we see that Zin will be equal to Z naught times, now this minus sign here, we send it to the bottom side here, so this will be equal to 1 plus gamma x divided by 1 minus gamma x. Okay, so this is the impedance at any point along the line. So all we had to do was to use the previous formula and substitute Z in for ZL and then solve for Z in. Okay, so now the next step is to substitute gamma x into here. So remember, what is gamma x? Gamma x is this formula here. So let us just copy this to the bottom here. And now we substitute gamma x into this formula. So Z in will be equal to Z naught times 1 plus gamma naught times e to the minus 2 gamma x divided by 1 minus gamma naught times e to the minus 2 gamma x. So this is Z in right here. Remember that gamma is equal to alpha plus j beta, and if you remember, beta is equal to omega times the square root of LC. Alpha also has its value. It's a bit more complicated to calculate. Perhaps in another video I will calculate it for you, but we can assume that alpha is 0 in most cases for a lossless line. So what else can we do with this formula here? Let's see. Let's first of all let alpha equal 0. So we can rewrite Z in to be equal to Z naught times 1 plus gamma naught times e to the minus 2. And now alpha is 0, so this is just equal to j times beta. So this is j times beta times x divided by 1 minus gamma naught times e to the minus 2j beta x. Okay, so now if you remember, there is a function in mathematics which is called the hyperbolic tangent. We write it as tang, and this tang is equal to e to the 2x minus 1 divided by e to the 2x plus 1. If you see here, I have a Wikipedia page which gives all the hyperbolic functions. So if you look here, tang x is equal to e to the 2x minus 1 divided by e to the 2x plus 1. So it's exactly what I have here. So we can use this formula. Here we can use this formula on this side here. So first of all, let us substitute for gamma naught. Remember that gamma naught is equal to ZL minus Z naught divided by ZL plus Z naught. So let us substitute that into here. So we get Z naught times 1 plus ZL minus Z naught divided by ZL plus Z naught times e to the minus 2j beta x. All of this divided by 1 minus ZL minus Z naught divided by ZL plus Z naught times e to the minus 2j beta x. Now we multiply both sides of this equation, top and bottom, by ZL plus Z naught. So this is equal to ZL plus Z naught plus ZL minus Z naught all times e to the minus 2j beta x divided by, and let's not forget the Z naught in front here. So here we have ZL plus Z naught minus ZL minus Z naught times e to the minus 2j beta x. So now this is equal to Z naught times ZL plus Z naught plus ZL times e to the minus 2j beta x minus Z naught times e to the minus 2j beta x divided by ZL plus Z naught minus ZL e to the minus 2j beta x plus Z naught e to the minus 2j beta x. Now we can factor ZL, so this is Z0 times ZL times 1 plus e to the minus 2j beta x plus Z0 times 1 minus e to the minus 2j beta x divided by ZL times 1 minus e to the minus 2j beta x plus Z0 times 1 plus e to the minus 2j beta x. Okay, so now we have to transform this into a form which is similar to the tanh function. Remember, the tanh here is e to the 2x minus 1, etc. So this in this case here, we multiply first of all we multiply hold on, e to the minus 1 minus, we multiply both sides of this equation by let me see, hold on, let me divide both sides of this top and bottom by 1 plus e to the minus blah blah. So Z0, it's because I'm running out of time here. I have 4 minutes left for the video, so this is ZL, we divide top and bottom by this term, plus Z0 times 1 minus e to the minus 2j beta x divided by 1 plus e to the minus 2j beta x divided by ZL 1 minus e to the minus 2j beta x divided by 1 plus e to the minus 2j beta x plus Z0. Okay, so now we have this, and this is almost equal to the tanh function, but we have 1 minus here instead of e to the e minus 1. So this, let me see, this is equal to Z0 times ZL. Now let's multiply this by minus 1, so this is minus Z0 times e to the minus 2j beta x minus 1 divided by ZL times e to the minus 2j beta x minus 1 divide, oh, I forgot the, hold on, I forgot the, to divide this side by, so this minus 1 divided by e, hold on, divided by 1 plus e to the minus 2j beta x divided by, this is now just this, which is Z0. Now multiply this by minus 1 minus e to the minus 2j beta x minus 1 divided by 1 plus e to the minus 2j beta x. So this is the Z0, which multiplies both sides. So let me put bracket here. Okay, so now if you look here, this is the tanh function, e to the minus 2j beta x minus 1 over e to the blah 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 plus 1, and same here, so we can substitute here for tanh. Now the tanh of this, remember that the tanh will tanh x will necessitate an e to the 2x minus 1 over e to the 2x plus 1. So here we have all of this, which the x here is the minus j beta x. So okay, so I'll finish this on the next video because I only have 1 minute left on this video. So I'll see you in the next video and we'll finish deriving this equation here.